The Chapter 4 of Hydrology is all about rainfall-runoff relation. The rainfall-runoff relation for any rainstorm depends on the interaction between the rain intensity, soil infiltration, and surface storage. First, we will define runoff. As precipitation falls towards the Earth's surface, a portion of it is intercepted by vegetation, surface retention, and soil moisture. The water intercepted is returned by the leaves and stems by vegetation. Depression storage includes water retained as puddles in surface depression, and the soil moisture is held as the capillary water in the smaller pores of the soil. The excess water may follow different paths. It can be determined as surface runoff, direct runoff, or groundwater runoff. So the surface runoff, this is the excess water that flows across the ground surface to the nearest channel. And for the direct runoff, this is the water that reaches the stream channel shortly after it falls to the Earth's surface, and it is completely discharged from a drainage basin within a few days. The direct runoff is also called as the overland flow. And the last is the groundwater runoff. It usually takes a longer period of time for the groundwater runoff to reach the stream, and this is the portion of water which percolates downward through the soil and reaches the groundwater that may eventually reach the open stream channel. And there is a technique that was developed as a standard means of runoff analysis, and this is the hydrograph. Hydrograph is a graphical representation of the time distribution of discharge at a particular location in the flow path. A typical hydrograph results from a single storm analysis that has a rising limb, peak, and recession. This is the rising limb. It has a peak and the recession. One of the simplest methods, and one that is as easily justified, is to conduct a straight line from the point at which the rising limb begins to the point of the greatest curvature on the recession side. The area between the curve and the straight line represents the volume of the direct surface runoff, and the area below the straight line is the contribution to the stream flow from the groundwater runoff, or also known as the base flow. So this is the base flow, and this is the direct surface runoff. Again, it has a rising limb, a peak, and a recession. And a unit hydrograph is a time-dependent surface runoff concept that may be expressed in terms of an equivalent depth resulting from a uniformly distributed precipitation over the watershed area. It is the runoff volume resulting from a rainfall equivalent to a depth of 1 centimeter of water over the whole basin, and net runoff multiplied by unit hydrograph is equal to the direct surface discharge. In applying an existing unit hydrograph, we need only to measure the net runoff in cubic meter to determine the discharge. The derivation of a unit hydrograph involves basically 4 steps. First is to select a reasonably uniform storm for which reliable rainfall and runoff data are available. Second one is to separate the runoff hydrograph into a direct surface runoff and base flow. Determination of the direct surface runoff hydrograph by subtracting the base flow from the runoff hydrograph. Determination of the volume of the direct surface runoff by planimetry, written in cubic meters net runoff, and The determination of the ordinates of the unit hydrograph by dividing the ordinates of the direct runoff hydrograph by the volume of the direct runoff. The resulting unit hydrograph should represent a unit volume runoff from the drainage area. So to further understand these steps or to apply these steps, let us proceed to our example number 1. Stream flow data were recorded for a storm whose effective duration was 12 hours. The drainage area to be site of the measurements is 1,150 square kilometer. Construct a unit hydrograph for this 12-hour duration storm. Moving these data to our Excel application for a faster computation. The first column represents the 4-day period. The second column is the time in hours since the rainfall began. And next is the recorded discharge in cubic meters per second. While the next one is the estimated base flow in cubic meter per second also. And to obtain the direct runoff, just need to subtract the discharge to the estimated base flow. And doing it to the rest of the cell, we have these values. And we can see that on the last hour of the 3rd day and on the 5th day, the discharge or the direct runoff would now be equal to 0, meaning it has completely discharged the water to the drainage basin. And then having our time after start, so we just need to subtract again the span of time between discharges. So for 4th day, we will leave it blank since there are no more direct runoff. So we will now take the summation of the direct runoff. Because to be able to determine the unit hydrograph ordinate, we need to divide the summation of the direct runoff to the total direct runoff area, or the drainage area I should say. So we have 3,435 cubic meter per second. And here is now the formula. I just converted 3,435 cubic meter per second into cubic centimeter per hour. So be informed that in solving this one, the units must be in uniform or must be in uniformity. So calculating the quotient, so the unit hydrograph coordinate would now be equal to 6.45 centimeter. And we now have a graphical representation of the recorded discharge and the unit hydrograph. It shows here the relationship between the recorded discharge in cubic meter per second and in that 4-day period in every time or in every 6-hour period. And we have here our recorded discharge from the data given. And we have here the unit hydrograph, and it can be obtained by dividing the direct runoff to our unit hydrograph coordinate, which is 6.45, and doing the same process for the rest of the data. So as you can see, on the first 6 hours, the unit hydrograph is equal to 0, and on the next 12 hours, the unit hydrograph is around 37.67 cubic meter per second, and the unit hydrograph is represented at the right part here. At the right part, this is the unit hydrograph, and the same on the 18th hour, it is around 90.7 cubic meter per second, and the rest of the data. Also have the peak, it's around 125. And for our next example, the basin in example 1 recorded a storm that produced a 5 cm runoff in the first 12 hours and a 3 cm runoff for the subsequent 12 hours. Calculate the hydrograph expected in this storm. And moving the data again to our Excel file. And the first column shows the time in hours since the rainfall began. The second one is the recorded discharge in the first 12 hours of a storm beginning at time 0. Next one is the 3 unit hydrograph, or a discharge related to the second 12 hours of a storm beginning at the 12th hour. And column 4 is the estimated base flow from conditions existing before the storm began. And to determine the total discharge, we just need to sum up the 5 unit hydrograph, 3 unit hydrograph, and the estimated base flow. So it's very easy. We are just adding the data. And we now have the total discharge. And for the graphical representation, we have here the graph for the total discharge, the 5 unit hydrograph, and then the 3 unit hydrograph. It shows here the relationship between the discharge in cubic meter per second and the time in hours. So for the first graph, the total discharge, so as you can see at time 0, the total discharge is 190. At time 0, the total discharge is 190. At the 6th hour, it is around 386.5, and the rest of the data. And for the 5 unit hydrograph, you can see the discharge, the discharge at time 0 is also 0. At the 6th time, it is around 188.5, and at the 12th hour, it is around 453.5. Also with the 3 unit hydrograph, same process, just need to plot the relationship between the discharge and the time. And connecting a straight line from the point at which rising limb begins to the recession side makes up the estimated base flow. So at this part again, this is the This represents the volume of the direct surface runoff, and at below of the straight line is the groundwater runoff, or the the base flow. Frequency analysis provides information for estimating the probability of future occurrence based on past data of a particular event recorded, and these events includes magnitude of floods or intensity of precipitation and others. The probability of an event of the same magnitude or higher can be calculated using this formula, in which the probability is equal to the order of assigned recorded event divided by the total number of events plus 1. And the calculated frequency of an event of the same magnitude or higher can be calculated using this formula. And in engineering hydrology, it is necessary to predict the discharge hydrograph of a flood with a downstream site based on the discharge hydrograph obtained from an upstream station. And this procedure involves flood prediction, or also known as the flood routing. So flood routing may be applied to predict the flood discharge or stage at any downstream station in a stream channel. It may also be used as a tool for analyzing the function and operation of an outlet structure in a proposed reservoir. So here is a simple equation that represents the relationship of continuity between two stations of the upstream and downstream ends, where I is equal to the inflow multiplied by the change of time is equal to the outflow in unit time multiplied by the change of time plus the change in storage in the reach during the time period. And it also be rewritten when the increments of time are sufficiently short. So we have two datas of inflows, or getting the average of the inflows and the outflows, and the difference of the change in storage in the reach during the time period. In a typical flood routing problem, the inflow hydrograph is always known along with the initial values of outflow 1, and the storage represented as S1. So rearranging the equation gives this formula. And in stream routing, the storage in a reach of the stream channel may be expressed as the storage is equal to the time period multiplied by the outflow plus the time period multiplied by the difference of the inflow minus the outflow. And here is an illustration that represents the equation. So for the first term, or the first term, we have here the prism storage. Prism storage is the product of the time period and the outflow in unit time. So this is the prism storage, and the second term is the product of the time period and the difference of the inflow and the outflow. This is also called as the wedge storage. So we have here a certain time period and the difference of the inflow and the outflow that will make our wedge storage. This represents the increment of storage in addition to the prism storage, resulting the difference of the inflow and the outflow. So again, on this part, this is the prism storage, and on this part, this is considered as the wedge storage. So the following equation can be calculated to be used in our outflow hydrograph. And to determine the values of K and Phi for a channel reach, field measurements must be made to obtain data of the inflow and the outflow using this formula. Also, kindly remove this equal sign here. It must be only plus sign. And the values of channel storage can be determined by this product, that the summation of the difference of the inflow and the outflow multiplied by the change in time would be equal to our channel storage S. So again, here's the equation of the channel reach and our formula for the channel storage. And to further understand about flood routing, let us have our first example. So determine the K and P values for a reach of a river. Field measurements are shown in column 2 and column 3. And moving this data again in our Excel file. Our first column shows the time, and the second is the inflow and outflow field measurement in cubic meter per second, and for our delta S value, we will be using this formula in which our inflow minus outflow would be multiplied by our time in per day basis. And doing it to the rest of the cell. And for our storage in cubic meter per second per day, we'll just take a cumulative process. So for the first cell, it is equal to 0, and then the next one 0 plus 27. And the next one is 27 plus 80.5. You're just taking the cumulative. Ayan. And for the column F, G, and H, we will be using that formula in which the phi is equal to 0.2 multiplied by the inflow plus the sum of 1 minus our phi, which is 0.2 multiplied by the outflow. Same process again. And for the next column, change lang natin yung values ng phi, which is now be equal to 0.25 yung phi natin. And for the last column, change lang natin yung phi into 0.3. Ayan. And we have our graphical representation here between the storage and the 3 columns at the rightmost part, with the corresponding storage at the respective value of phi. So they are all in cubic meter per seconds per day. And on the first graph, or on the third graph rather, we have our slope, which is 1.06. We are just taking a straight line from the graph to determine the slope. And for the next problem, with the K and phi values obtained in the first problem, calculate the outflow hydrograph for the channel reach with the inflow hydrograph provided in the table. Compare the inflow and outflow hydrographs. So we will be using this formula in determining the channel reach and here is the data provided. And we now have here the 3 formulas in obtaining the channel reach, in which our K is equal to 1.06 and phi is 0.3 plus 1/2. Since our basis is per day, so we will convert our 12-hour period into a day, so it's 0.5. So our channel reach is equal to 0.573. And for our channel reach 2, it is equal to negative 0.069. And for our C3, it is now equal to 0.496. Multiply natin siya by 93. And for C2I, multiplying C2 by our discharge at the second 12-hour period, so it is equal to 93. So drag it down, same process lang. And our outflow here is 48, so we'll multiply with C3 by the outflow at the first hour. And to determine the next outflow, I just need to add C, D, and E. And then same process ulit. The outflow multiplied by 0.496. And then taking it the sum of C, D, and E. Ayan. So same process until the end. Ayan. So I'll just convert it into a 2 decimal places only. Ayan. And now we have here our graphical representation of the graph showing the inflow and the outflow. We have here the relationship of discharge and the time per hour. Here is the inflow and the graph for our outflow.